right, up on the board here I've got two problems that look fairly similar. They're both indefinite integrals of a fraction where I've got 1 plus the quantity 2x squared in the denominator. Here I have a 1 on the top, here I have an x on the top. So turns out we're going to do things fairly differently. We are going to do each of these with a u substitution. What I'd like you to do is pause the video and see if you can figure out how to do one or both of these. Both would be preferable, but if you just get one, that's okay. This is kind of tricky. Pause the video, give it some thought, then tune back in and we'll work through things together. Welcome back. Okay. So here, I think it's actually helpful that we have the 2x in parentheses like that. Because when I see 1 over 1 plus something squared, I recognize that if I had just a plain old x there, that would be the derivative of arctan. So it looks like this is the derivative of arctan, but evaluated at 2x instead of x. So it seems reasonable that I would let u be 2x. U prime then would be 2. Now I don't have an extra 2, but I can multiply by 1 in the form of 2 halves. And what I'm doing here is I'm just multiplying by 2 on the inside, and I'm counterbalancing with a 1/2 on the outside. Remember, that's totally fine as long as what I'm multiplying by is a constant. I'm technically multiplying by 2 and 1/2 both on the inside, so that I'm multiplying the inside by 1, and then just factoring out that extra constant of 1/2. Okay, so with that, this becomes 1/2 the integral of 1 over 1 plus u squared du. I forgot to finish writing that du is going to be 2 dx, so those two pieces become my du. And then this is just 1/2 arctan of u plus c, and that's going to be 1/2 arctan of 2x plus c. Okay, now for this one, I actually don't think it's particularly helpful that we've got the 2x in parentheses like this. I think for this one it's easier to see what to do if I multiply that out and say that denominator is 1 plus the quantity 4x squared. So let's not forget, this is a math class. We are allowed to do the math. So sometimes doing some arithmetic or some algebra that's involved in the problem makes it easier to recognize what's going on. Okay. Now here I've got this x squared as part of the bottom, and so I'm thinking maybe that x is going to be part of the derivative. I'm going to try making the entire bottom be my u. Then u prime would be 8x, and du would be 8x dx. So I'm going to need an 8, but I can counterbalance with a 1/8 on the outside. And then the 8, the x, and the dx all become my du. So this is 1/8 the integral of 1 over u du. And I can integrate that because that's just the reciprocal function. You might have been tempted to let u equal just the 4x squared. If you did that, actually just to make it different, I'll make it w. W prime would have still been 8x, dw would have been 8x dx. The problem is I could have done this still 8 and 1/8, but when I do that I get 1/8 the integral of 1 over 1 plus w dw. Now 1 plus w, the reciprocal of 1 plus w is itself a function composition, because that's w, or sorry, that's 1 plus w plugged into the reciprocal function. So by letting the entire bottom be my u, I got just a simple function of 1 over u. Now, if I had done this and I had this, that would be okay. I just need to do a second substitution. Maybe let v equal 1 plus w, and then the integrand would become 1 over v. But here, I sort of could see, oh, I'm going to get just the reciprocal function if I let my u be the entire denominator. All right, so then this is 1/8 natural log. Do not forget the absolute value of u, and then plus c. And so that's 1/8 natural log absolute value of 1 plus 4x squared plus c. Now at this point, I might notice 1 plus 4x squared is always bigger than 0. That's always going to be something positive. So taking the absolute value isn't going to change it. So I could say this is just 1/8 natural log of 1 plus 4x squared plus c. In this case, I can actually evaluate that absolute value, like so. Okay. But just a word of caution, I can't tell the difference between you remembering the absolute value and noticing that that's always positive and evaluating the absolute value and you just forgetting it. Okay? So anytime you're integrating the reciprocal function, I want to see that absolute value. If you're subsequently able to evaluate it and explain, hey, the reason this is going away is because I'm evaluating it because that's going to be always positive, that's totally fine. Okay? But I do want to see that work as you're doing problems like this.